Okay, since a lot of you had asked for some feedback on how you had or how to do lab one essentially from chapter one, data storage, I put together a PowerPoint to explain some of the things um, that you were having trouble with. And a lot of these are in the book, and I'm going to try and refer to some of the page numbers that I can find here. So the first problem is are these gates. Okay, and if you look on page 22 and 23, 22 has the gates and the corresponding inputs and the outputs. So your question is, if the input, the upper input was 1 and the lower input is 0 for each one of these circuits, what do you get? So if you look at the gates and look at page 22 in the 12th edition or the corresponding page in your 11th edition, this gate is an XOR gate on the top and this is a NOT gate. So if you have a 1 in the upper input, that goes right into the XOR, and the 0 goes through a NOT, so it becomes a 1 when it goes into the XOR. So we all know if you look at the XOR input output, a 1 and a 1 at the input gives you an output of 0. So there is a 0. Now for B, you have an OR gate and an AND gate. So we have 1 going into the OR gate and a 0 going into the OR gate. And according to our table, a 1 or 0 gives us a 1 for the output. And then we have the 0 going straight into the AND gate. So 1 and 0 will give us a 0 for the output. In C, you have a 1 and a 0 again, and we have two XOR gates. So the 1 goes directly into that XOR, and the 1 also comes to this XOR here, and we have a 0 going into this XOR. So 1 XOR 0 is a 1. Remember, when they are mutually exclusive, we get an output of 1. And the 1, when it feeds into this other XOR with the other 1, will give you an output of 0. So I have only explained one of these. You can do the second one exactly like the first one. You just have to read through the pages and follow some of these steps. Okay. So the next one I've explained is problem number 5. Problem number 5 says you're given this list of address and the contents. Now what happens when you do some of these steps? And the first step says move the contents of the cell whose address is 03. So here's the address 03. The contents of that cell is 02. And we want to move that content to the content of address 00. So this is what we do. So we move 02, which is in 03, and we replace AB with 02. Notice nothing happens to the other cells. They all remain exactly the same. Step 2 says move the value 01. That means the literal value 01 into the cell at address 02. So here's my address 02. Now its value has become 01. Notice everything else remains the same. We have a 02 and 00, which we did the previous step. 53 was already there, and 02 and 03 was already there. The next step says move the value stored at address 01, which is 53, into cell at address 03. So we are going to replace that 02 with 53, and this is what we end up with. And so when you move, you really don't change any of the other cells. You simply move and replace the existing cell value. Now I'm going to do number 26, which says you take each of the following binary representations to its equivalent base 10, which is our decimal. Easiest way to do this is just like decimal is powers of 10, binary is powers of 2. So we start with 2 to the power of 0, that's 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. So the powers go 0, 1, 2, 3. The base is 2. So 2 to the power of each one of those numbers, these are the numbers that we are looking at. That's our base, okay? That's what we're going to use. Then we need to convert the first one that says 1, 1, 1, 1. That's a binary number. So we have a 1 in each one of these places. So you simply take 8, you add 8 plus 4 plus 2 plus 1, and that gives us 15. Now take a look at the next one, which is 6 bits. We have a 1 only in the position of 32 and 1. So the number is 33. 32 plus 1 is 33. Like I said, the Virginia Tech Materials has more information on this, so please do look at that when you get a chance. The next one is problem number 30. Now this is where you take 2's complement representations to its equivalent base 10 representation. Now the reason this is a little tricky is it says it's 2's complement. When it says it's 2's complement, we know that some of them could be positive and negative. Like it says A and C have a 0 in the most significant bit. So we know they are positive numbers, they are straightforward conversions. But B, D, and E have a 1 in the most significant bit. So they are negative numbers, and to convert them you must do 2 steps. You must first flip the bits. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. Then you add a 1 to the rightmost bit. Then you convert from binary to decimal and add a negative sign to it. So here's the first problem, 10100. The first step is to flip the bits. You get 01011. Notice they're just the opposite. Then you add a 1 to the rightmost bit. And if you do your actual binary addition, add a 1 to the rightmost bit, you get 01100. If you take that, its binary equivalent is 12, but since the most significant bit is a 1, you get minus 12. So that kind of shows you how to do some of these conversions. I will post this PowerPoint so you can look through it, and I will try to do this for a couple of more chapters where you need to do some computations, and let me know if that helps.